Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'll talk about higher order Cheeger inequalities and for graph multi-partitioning problems. So firstly, what is graph partitioning? Right, so you're given a graph and you want to partition it into some pieces. And generally how a measure of how good the partition is some function of the edges that go between the pieces and the sizes of the sets. Okay? So one of the most well-studied problems is the sparsest cut problem, where you are given a graph, and for any set S, we define its expansion as the ratio of the edges that go out of the set divided by the size of the set. Okay? And we denote this by phi of S. And the expansion of the graph is the minimum value of phi of S over all sets S of size at most n over 2. Right? Clear? So this is a fundamental NP-hard problem, and it's sort of interest to the Markov chains people, because if you were to do something like a random walk, then the mixing time of the random walk depends on the expansion of the graph. And many of these divide and conquer algorithms go like you first find the sparsest cut, recurs on both pieces, and so on. So trying to compute the sparsest cut is a very important NP-hard problem. So there's this thing called Cheeger's inequality, which is a very fundamental way of measuring the expansion of the graph. So the Cheeger's inequality says this. So you look at the Laplacian matrix, which is, for a d-regular graph, it is the identity matrix minus the adjacency matrix divided by d. So see, this matrix is symmetric and diagonally dominant, right? It's easy to see that the smallest eigenvalue of this matrix is 0, right? So you just take the eigenvector with the all ones vector, and that is an eigenvector with eigenvalue 0. And a very simple exercise to show is that if your graph has something like k connected components, then the first k eigenvalues are all 0. Okay, so what Cheeger's inequality says is that you look at the lambda 2, the second smallest eigenvalue, and the expansion of the graph is at least lambda 2, and at most 2 times square root lambda 2. And the proof of Cheeger's inequality also gives you an algorithm to find a set which satisfies this upper bound. So you sort the entries of the second eigenvector in decreasing order, let's say x1 through to xn, x1 being the largest and xn being the smallest. And you look at the cuts defined by this ordering. Okay? So Si is the set consisting of the first I vertices in this ordering. Then the proof essentially says that the minimum of phi of Si over these i's is at most 2 square root lambda 2. So it gives you a simple algorithm to find a set which satisfies this upper bound. Okay? So in this talk, I'll talk about 2 problems. You are given a parameter k, and the first problem is to partition the graph into k pieces so as to minimize the maximum over I of phi of Si. And the second seemingly easier problem is to find a k-partition that minimizes the total fraction of edges that you cut. Okay? So it's easy to see that whatever upper bound you prove for the first problem will also be an upper bound for the second problem. So the second problem is an easier problem. So let's do that first.
Total fraction of the edges cut.
Yeah.
Why is it easier?
I mean, so whatever upper bound you prove for the first problem is an upper bound for the second problem, right? So the first problem, I want you to find a k-partition, S1 to Sk, so as to minimize this term, max over I of phi of Si.
So really, I mean, in one case you partition, you maximize or care about a single number, and in the other case, in a way, you care about k numbers. I mean, not in this particular case, but there are many questions in extreme graph theory where you want to say something about all the numbers involved, so not even k, but like interest. You would like to know how many edges go between any 2 classes, and so it's much harder.
But the upper bound, the upper bound is not in terms of optimal of means.
Right. I'm just saying it's like a spectral upper bound, something like in terms of function of k or lambda k or something.
The objective you mean, or like when you say upper bound, or is it the solution you're talking about, or the number you're talking about?
The number. So the total number of So suppose you prove that this term is at most, say, some alpha.
Okay, good.
Then I'm saying that the upper bound here is also at most alpha.
Not the approximation ratio, right? So
No, not the.
I'm just talking about absolute numbers, not approximation factors. Okay.
So, like, okay, good.
So for the first problem, so there's a very simple recursive algorithm, right? So the Cheeger's inequality gives you a way to find one cut. So you find that cut, remove those edges, and add self loops in their place. Okay. For each edge uv that you remove, you add a self loop at u and a self loop at v. And then you repeat. Now we have two pieces. Look at which piece has the smaller second eigenvalue, and do this again till you get k pieces. And I'll show you that this very simple algorithm cuts at most square root lambda k times log k fraction of edges. Right? So this is an absolute upper bound. It's not like a approximation factor or something. Okay. So to prove this, there's the first interesting observation is that if you remove any edge from the graph, your eigenvalues are only going to decrease. Okay. So I'll prove this for you, and it's a very simple thing. So first note that, so let C be the set of edges that you're removing. Then the adjacency matrix of G minus C minus the adjacency matrix of G is a diagonally dominant matrix.
Okay, when you say eigenvalue, this is of the Laplacian.
Yeah, of course. Sure, yeah. So do you see why the adjacency matrix of G minus C minus the adjacency matrix of G is a diagonally dominant matrix? So which entries do these two matrices differ in? Only the entries corresponding to the adjacent C, right? Everything else is the same. So in this difference, you'll get a -1 for every edge that you removed. But for every edge that you removed, you also added self loops at both the endpoints. So you'd get a +1 in the diagonal entries corresponding to them. Right? So this is a diagonally dominant matrix. And all diagonally dominant matrices are also.
Sorry, silly question, but a diagonally dominant matrix is something where values on the diagonal beat the sums of things.
Yeah, so for every.
So in the adjacency matrix, you have degrees on the diagonal?
Yeah.
Okay.
So diagonally dominant, I mean that the I comma ith entry is larger than the sum of the ith row and larger than sum of the ith column.
So in the adjacency matrix, the I comma I entry is the number of loops.
Yeah, that's what I mean, yeah.
So when you normalize, so after you remove a cut, the graph is no longer.
No, so I'm adding self loops in their place, so it's still deregular. So when I'm counting the degree, I'm counting the self loops also. Right? So it's deregular, so it's diagonally dominant and positive semi-definite. Okay, so let k be an arbitrary number. So the kth eigenvalue of G minus C is given by, you minimize over the subspace of rank k. And within that subspace, you maximize x transpose, the Laplacian of G minus C times x divided by x transpose x. Right? So let me just rearrange the summation and write it this way. Right? So the Laplacian of G and G minus C differ in exactly this term. And what is this? So this is a PSD matrix, right? So this term is always going to be non-negative. So let me just throw that term away, and I get a less than equal to. And what is this term now? It's exactly lambda k of G, right? So I just proved to you that if you remove any set of edges, the eigenvalue is only going to increase. Each eigenvalue can only decrease. It cannot increase. So what does this mean? So when I'm making the ith cut in my recursive algorithm, I can bound it by lambda I of the original graph, which is at most lambda k of the original graph. Right? So each cut I can upper bound by square root lambda k times size of the smaller side. Okay? So the total fraction of edges that I'm cutting is at most 2 times square root lambda k times summation over I of Si. So I should have said this before. So the notation I'm going to use in this talk is that Si is going to be the smaller side of the cut, and Si complement is going to be the larger side of the cut. Okay? So the total fraction of edges that I'm cutting is square root lambda k times summation over I of cardinality of Si, right? So I just need to show that now that the summation of over I of the cardinality of Si is at most the size of the graph times log k, right? If I show that, then I'm done. So this is a simple counting argument. To show this, I'll construct a tree on k nodes of size log k, which has the property that if you look at any level, the sum of weights on those levels is going to be at most order e. Okay? So I'm going to construct a tree on k nodes. On each of these nodes, I'm going to put one of the SIs. So I said the trees of height log k, and the summation of weights on each level is something like order size of the graph. If I can show such a tree, then I'm done, right? Because that shows that the summation of these SIs is at most e times log k. Yeah. So as a first attempt, let me use these rules to construct a tree. So I'll make Si the child of Sj if Si is obtained by cutting the smaller side of the previous cut. Otherwise, I'll make it a sibling of Sj. So let me illustrate it with a picture over here. So in this graph, so I'll put V as the root of the tree. And the first cut I make is a trivial cut, so let me just make it the child of V. Now the second cut that I make is obtained by cutting S1 complement, right? So using the second rule, I'll make it a sibling of S1. Now the third cut that I'm making is obtained by cutting S2. So by the first rule, I'll make it a child of S2. And the fourth cut I'm cutting is obtained by cutting S1. So again, by using the first rule, I'll make it a child of S1. So at this point, you could probably see where I'm going with this, right? If you look at any level, the sets that I'm putting there are already disjoint. So the sum of weights at each level is at most E by construction, right? But as you can probably imagine, the height of this tree could be huge. I mean, it could be as large as k if each time you were cutting the same size, the smaller side of the graph, right? But note that the tree that I constructed has this property that every node is at most half the weight of its parent, right? So I can use this to shrink the size of the tree. So suppose my tree looks like this. Suppose my tree has a long induced path in it. I know that each of these nodes is at most half its parent because it was obtained by cutting the parent, and I'm only putting the smaller side of each cut in the tree. So suppose I were to shift all of these things up. So how much is this thing going to increase by? The summation of all these blue things is at most the largest blue thing over there, right? So at any level, the summation of weights is at most going to double. It's still going to be at most 2 times the size of the graph, right? And now the tree also has the property that every non-leaf node has degree at least 2. So its height is also log k, right? So yeah, therefore we are done. So the summation of all these SIs is at most E times log k. And as I showed you before, the total fraction of edges we cut is now some order lambda k times log k. Any questions?
How tight is it?
Yeah, it's not tight.
Like, what is a lower bound? Like, is there any lower bound?
Yeah, so the only lower bound you can prove is lambda 2, unfortunately. So this is not tight at all.
But you know, if phi sum is 0, then lambda k is also 0, right?
Yeah.
So, but can't you put a function, some function of lambda k?
Or you can put something like lambda k over k if you want, but that could be very small. So you cannot put a lower bound, but a tight example is that there is no tight example, but there exists a family of graphs for which this value is square root lambda k log k. The log k is under the square root.
Okay,
so this is not tight.
So in a sense, square root lambda k of log k, everything over is tight. You can't improve that bound.
Yes, you cannot improve that bound. So yeah, But another thing is that any of these, the partition that you obtain here could have, the individual sets themselves could have very bad expansion. Right? In general, you cannot say anything about their expansion. So that's what I'm going to talk about next. So in the graph G, if you pick any k non-empty disjoint subsets, then at least one of them will have expansion lambda k. Okay, so this is similar to the easier part of Cheeger's inequality, where you show that the expansion of the graph is at least lambda 2. And probably the more interesting part is that there exists a 1 minus epsilon k partition, S1, S2 up till S1 minus epsilon k, such that each set has expansion at most square root lambda k log k. Okay, so this is similar to the harder part of Cheeger's inequality, where you show that the expansion of an edge, the expansion of a set is at most square root lambda 2. And yeah, in this case, these two bounds are tight. The lower bound is tight if you take the Boolean hypercube, and the upper bound is also tight for. Oh, I should also say that this theorem was independently proven by Garan, Lee, and Trevisan also. Okay, so the upper bound is tight for what is known as this noisy hypercube. So basically you take the vertices of a Boolean hypercube, k-dimensional Boolean hypercube, and put a complete graph on it. And the weight of an edge xy is like epsilon to the Hamming distance between x and y. Okay. So at this point, it's easy to show that the first k eigenvalues are at most epsilon. And with a little bit of work, you can also show that any set of size at most 1 over k will have expansion at least square root epsilon log k. So this follows from some Fourier analytic tools, and more specifically what is known as the reverse Bonamy-Beckner inequality. Right? So if you find a k-partition, then at least one of these sets is going to be smaller than 1 over k. Therefore, this is really the best you can prove for a k-partition. Okay. Okay, so first let's do the lower bound. The lower bound is the easy part. So you want to find, suppose you let S1 to Sk be some k disjoint subsets. And again, so we know that the lambda k is obtained by minimizing over rank k subspaces. And within that subspace, maximizing x transpose Lx divided by x transpose x. So what is the t that you're going to plug in over here? Well, there is only one thing you can do, right? So you take t to be the span of the characteristic vectors of S1 through to Sk. And this is going to have rank k. And at this point, you can essentially show that the vector which maximizes this term has to look like one of the characteristic vectors of this set, or something like very similar to that. So that is roughly a main idea of the proof. Okay. Okay. So for k-partition, I told you that you can obtain a 1 minus epsilon k partition such that your expansion is like poly 1 over epsilon times square root lambda k log k. So you really cannot do away with the poly 1 over epsilon over here. You really need that thing over there, because in general, if you wanted an exact k partition, then there exists a family of graphs for which max of I over phi of Si can be much, much larger than square root lambda k, as large as k squared divided by square root n. So the family of graph essentially looks like this. You start with a k cliques and a central vertex, and then you add edges between the central vertex and every other vertex individually with probability p. Okay, so I get an upper bound on lambda k from the inequality I showed you in the previous slide. These k sets have small expansion, therefore lambda k has to be small.
Sorry, the SIs are complete, did you say? What are they?
The SIs are cliques, complete graphs.
But then what's the point of adding edges with probability?
No, I'm adding edges between this central vertex and every other vertex with probability p.
Yeah. Why don't you add a certain number of edges? What is the difference?
Okay, so you can say you can add. Well, I wanted to make it.
random edges to
No, I wanted to make it an unweighted graph. If you're fine with weighted graphs, then you can just put weights of edge p over here. No, I just wanted to make it an unweighted graph, so that was the point behind this.
I guess the point is that all vertices in the clique are identical, right? So instead of adding random, you can just add the edges to first.
So first
the first?
Edit the first.
No, well, if you add edges to one vertex over here.
No, to the first p and vertices.
Over here?
Yeah, because all of them are the same, sort of.
Right, so.
You can permute them, whatever.
Well, so if you add vertices, so I really want this to be uniform because, if you do something like that, add vertices to some vertex over here, then, so if you do it like this, then it's easy to argue what this value is going to be. It's easy to prove a lower bound on this. I mean, it should work if you do it that way as well, but I'm just saying, regular things look nicer.
Like are you thinking of them as weights? If you're
Think of them as weights. Think of this, all these edges having weight p.
No, but that's a different thing,
That's
right?
a completely different thing.
So that's a different graph, right? Than having a.
It's not a graph. You give weights to the edges. That's different.
So that's a single graph. But here now you have a distribution of graphs, but all of those graphs are kind of more or less isomorphic.
Okay, so let's just assume that these edges have weight p. If you're fine with weighted graphs. Yeah. Okay, so in that case, you can show that. So the central, in the k-partition that you're going to produce, you'll have to put the central vertex in some piece, right? And whichever piece you put it in, you're going to pay a huge expansion because the central vertex has a lot of edges incident on it. So suppose you put it in SI, then phi of SI with the central vertex is going to be like k times the expansion of the rest of the pieces. And this fact is enough to get a huge gap over here by appropriately choosing the value of p. Okay. Anyway, so the point I wanted to make is that you really need this poly 1 over epsilon here. You cannot place some small constant over there. I mean, as you get closer and closer to k, that thing has to blow up. Okay. Okay, so let's see how to prove this. So Cheeger's analysis essentially shows that you don't need to start with the second eigenvector. You can start with any vector x, which has small support, and you can obtain a set S which lies in the support of x, whose expansion is at most this quantity over here. Okay. So this quantity, I would like to think of it as the average distortion of the L1 embedding given by this vector. So the embedding is a canonical embedding, right, where you map vertex I to the value xi. So then this term xi minus xj is like the distortion of this edge. And what this term is like under some weird normalization, this is like the average distortion of this embedding. So Cheeger's analysis essentially says that you can start with any vector and find a set S which lies in the support of this vector and whose expansion is at most the average distortion. So if I can find theta k such vectors, each having disjoint support and each having average distortion, small average distortion, then I'm done, right? Because I'll plug in this lemma to each of these vectors, and each of them will give me a set. Right? So that's going to be my main goal for the rest of this talk, to come up with theta k such vectors which have disjoint support and have small average distortion. Okay. So I don't know how to start with such vectors, but the top k eigenvectors give me an embedding into R to the k, right? The canonical embedding, where you map the vertex I to the vector consisting of the ith coordinate of each of the eigenvectors. Okay. So this embedding satisfies some very simple properties. First one says that the summation of lengths of these vectors is equal to k. Right? So this just follows from the fact that you have k eigenvectors, each of them having length 1. And probably the most interesting property is this, that the average inner product square is equal to k. So this again follows from the fact that the k eigenvectors are orthogonal to each other. But the reason why I want you to notice this is that if you were, this is a very strong property. It is not satisfied by, say, some random vectors in r to the k. So if you were to pick some random vectors in r to the k and normalize it in this form, you would get that the average inner product square is like k square. So this thing being equal to k indicates somehow that there are already some clusters among these vectors, which we will crucially exploit later on. And this thing is also easy to see, that the average distortion of this embedding is at most lambda k, right? Well, this follows from the fact that each coordinate has distortion at most lambda k, because they are the first k eigenvalues. Okay. Any questions? No? Okay, so the rounding algorithm is very simple, probably very simple. You pick g random Gaussian vectors, g1 through to gk. Let x1 be the projection of all the vi's on g1. Let x2 be all the projection of all the vi's on g2, so on. Let xk be the projection of all the vi's on gk. And we wanted to make these vectors disjoint support, right? So what's the most obvious thing you would do? Go to each row and zero out all but the largest value. Okay? So let me look at the first row. Let's say the first value is the largest value. So I'll keep that and zero out everything else in the first row. Then I go to the second row, keep whatever is the largest value, and then zero out everything else. And I do this for each row. Okay? So yeah, so now I have k vectors, each of which have disjoint support. And now I need to show that all of them, or some fraction of them, have low distortion. Right? So is the algorithm clear to everyone, or any questions? Okay. So why does this algorithm work? So an intuitive reason why this works is that, so if you think of the blue vectors as the vi's and the brown vectors as the Gaussian vectors that you picked, then essentially what the algorithm is doing is that the support of your vectors is going to look like, the support of x1 is going to look like this thing, this cluster around g1, right? Roughly, or mostly. And the support of g2 is going to look like the cluster around g2, and so on. Right?
It's like a Voronoi diagram. It's like a Voronoi diagram. You take the closest to each of the k rows.
Yeah, so I'm sort of finding
the square distances.
Yeah, so I'm finding these clusters in. So I'm just saying that this algorithm that I did before is going to find these clusters, roughly, or some large fraction of this, and which is roughly what we want to do, right? Because I want to find these clusters, and if the clusters are sort of close together, then they would give us like good sets, or so on. Now that's what I'll prove. Okay. Okay. So roughly the analysis is going to go like this. So recall that to show that, so this is the term average distortion, and I want to show that this is small for a constant fraction of the indices, right? So I'll show you that the expected value of the denominator of each of these vectors is like log k, and the expected value of the numerator is like square root lambda k log cube k. Okay, so the ratio is like what we want. So is this sufficient for us? Probably not, right? So I'll also show you that the expected value of the ratio is bounded by some constant times the ratio of the expected value for some constant fraction of indices, which is like square root lambda k log k. Okay? So let's do the denominator first. That is the easy thing. So again, keep this picture in mind. So this is the first entry, and I did not zero this out, and I zeroed out everything else from the first row, right? So what is the probability that I did not zero this out? Well, all the GIs are independently chosen, so any of them could have been the largest. Probability that this is largest is 1 over k, right? And okay, so let's say I did not zero this out with probability 1 over k. And suppose I know that this is the largest in this row. What does its expected value look like? So this is a simple exercise. So if you were to pick k standard normal random variables and look at what is the expected value of the max, it is less than equal to 2 log k. Okay. So keeping this in mind, I get that the expected value of the first entry, or the expected value of the ith entry in the first column, is vi squared log k. I mean, condition on it being non-zero, condition on it being largest in its row. Okay, so its overall expected value is exactly this term divided by k. The expected value of the ith term is norm of vi squared log k divided by k. So to compute the expected value of the denominator, I just sum this over all entries, right? And recall that I had normalized the vi's in such a way that summation over I of di vi square was exactly equal to k. So the denominator is exactly equal to log k. Okay? Any questions? So this was the easy part. So the numerator requires a bit of work. So the numerator consists of terms which look like xi and xj, right? Xi minus xj. And as before, I can calculate the expected value of xi when xi is non-zero. And I can calculate the expected value of xj when xj is non-zero. Right? So here xi and xj are like norm of vi square times this vi tilde g1 square if this thing is the largest in its row. Again, so throughout all this, I want you to keep this picture in mind. This is the projections, and this is the thing that I did not zero out. Okay? So xi is like norm of vi square times this random variable if it is largest in its row, otherwise it's 0. And same thing is xj. So I need to calculate, so there are 4 cases here. Case 1, both of them are 0, which case I don't care, both of them are 0. Case 2 is then both of them are non-zero. Well, I'll ask you to believe me on this, but the probability of that happening is small. So that is probably not something you should worry about. The most interesting case is when one of them is 0 and the other one is non-zero. Okay, so we need to bound the probability of that event happening. So this is what it looks like. So there's this unit sphere. Vi tilde and vj tilde are vectors on this unit sphere. And I want to calculate the probability that xj is greater than or equal to 0 and xi is 0. Right? So suppose g1 were to look something like this. So when would xj be non-zero? So this would roughly be non-zero when vj tilde aligns very well with g1, right? So just keep this picture in mind. So this was my rounding algorithm. So when would v1 g1s be the largest in its row? So if it is the largest among all these projections, that means v1 is aligning very well with g1, or at least better than how much it's aligning with all the other GIs, right? So if say xj is going to be non-zero, then it means that most probably it is going to lie in this shaded region around g1 over here, right? Because if you could say that if it does not lie in the shaded region, then with high probability it is aligning with much better than with some other GI. Okay? So to calculate the probability that xj is greater than 0 and xi is non-zero, so that should depend on the distance between these two vectors, right? If these two vectors are very close to each other, then they would behave the same. Then these two random variables would behave the same. If these two vectors are orthogonal, then they just behave independently, right? So using this, you can show that the probability of a cut being made, in the sense that probability that one of them is 0 and the other one is non-zero, is upper bounded by 1 over k times the distance between these two vectors times square root lambda k. So the square root lambda k comes because it is like the size of the kth cap on the unit sphere. Okay? And this was formally proven by Charikar, Makarichev, and Makarichev. Any questions? Okay, so moving on. So now I'm ready to calculate the expected value of xi minus xj. So when xi is, say, 0 and xj is non-zero, the expected value of xj looks like this, bj square times log k. The probability of that event happening is this. And when the opposite event happens, xi is non-zero, xj is greater than 0, the expected value looks like this. And again, the probability of that happening is this, right? So, well, I'll ask you to bear with me on this slide. This is the only slide that has math on it, this much math on it. So by doing some sort of a simple rearrangement, I can upper bound it by this term, 1 over k times the sum of lengths times the distance between them times the log cube k. So I'm collecting this square root log k and this log k. Okay. So at this point, whenever you see a term that looks like this, it's sort of asking for you to plug in Cauchy-Schwarz inequality, right? You sum this over all edges and apply Cauchy-Schwarz over there. So what do you get? The 1 over k stays as it is. You get something like vi minus vj whole square summed over all edges times summation over I vi square. Right? And what was this value? So if you remember this picture that I showed you before, the summation over the edges of vi minus vj square is lambda k times this thing, and this thing is equal to k. So summation over I, summation of over edges of vi minus vj whole square is lambda k times k. Okay, so let me plug that in over here. So this is just lambda k times k. This thing was also just k. So the square root k and k cancels, and you are left with square root lambda k log cube k. Okay. So any questions? Okay, so let's do a quick overview. So we bounded the probability that xi, one of them is 0 and the other one is non-zero, which was this. And we know how to calculate the expected value of one of them and the expected value of separately. And I didn't show you what to do when both of them are non-zero, but that is a very simple case and happens with very small probability. So you can ignore that. So once you know how to do this, you just sum them over all edges, apply Cauchy-Schwarz, and then you're done. Okay. Okay, so till now I showed you that the denominator is log k, and the numerator is square root lambda k log cube k. And now I'll show you that for a constant fraction of the indices, the expected value of the ratio is bounded by some constant times the ratio of the expected values, which is square root lambda k log k. Okay. So again, so in this part we will crucially use this property that we had of our embedding, that the average value of the inner product square is like 1 over k. And so this already indicates that there is a high correlation into clusters, right? So as a thought experiment, just consider the following case when any two of the VIs are either same or orthogonal to each other. Okay. So any two Vi and Vj, they are either equal or they are orthogonal to each other. So in this case, I claim that the rounding algorithm is like throwing k balls into k bins. So what are the balls and bins over here? So the k bins are the k vectors that you have, and the k balls are the k clusters of the VIs that you have, right? And why is this like throwing balls into bins? So if you recall what our rounding algorithm did, so you took projections of some VI onto the GIs, and whichever one was the largest, you sort of assigned it to that vector, right? So the vectors are like the bins, and I say that my ball has gone into some particular bin if the vector that I picked is largest in that, the VI that I picked is largest in that GI, right? So the rounding algorithm is sort of like throwing k balls into k bins. And what happens when you throw k balls into k bins? You would expect that something like 1 minus 1 over e fraction of them are non-empty, right?
You have independence, right? You don't have independence, right? You have dependence.
No, so that's what I said. Assume for this experiment, consider a thought experiment where two VIs are either equal or orthogonal to each other. So in this case, when one vertex goes, the whole cluster goes with it. And since they are orthogonal, they are independent. This is just the intuition. And so in this case, you get that a constant fraction of the denominators are large. Like whenever one ball goes into a bin, that bin is like large. And so this is the intuition behind trying to show that the denominator is large, but unfortunately this does not work. It would have been, we could not make it work. It probably works, I don't know. We have to go through the boring way of trying to bound the variance of the denominator. Okay, so what does the variance look like? So the variance is the summation of expected values of xi and xj. And what does this term look like? So we know what is the expected value of xi when it's non-zero. It's something like vi square times log k. We know the expected value of xj when it's non-zero. It's something like vj square times log k. And what we need to bound is the probability that both of them are non-zero, right? So again, recall that xi was this random variable if the projection on G1 was the largest in that row, similarly xj. So I'll show you that the probability that both of them are non-zero can be upper bounded by the inner product of vi tilde and vj tilde whole square divided by k plus 1 over k square. Okay. So again, think of this picture in mind. So let's consider the two boundary cases when vi tilde and vj tilde are orthogonal to each other. Okay. So in that case, what is the value of this probability? So if vi tilde, vj tilde are orthogonal to each other, then these two random variables are independent random variables, right? Xi, xj are like totally independent random variables. So the probability that both of them are greater than 0 is 1 over k square, right? And the other boundary case to look at is, say, when vi tilde is equal to vj tilde. So in that case, what is the probability that both of them are greater than 0? It's just 1 over k, right? Which what we have over here. So essentially what this statement is saying is that the general case is a convex combination of the two boundary cases. The two boundary cases being when once they are both completely independent and one when they're like completely correlated. So proving this requires a bit of work, and I'm not going to prove it for you. You just have to believe me. So roughly a high level idea is that you can think of each xi as a function from the Gaussian space to the real line, right? So because each xi is a function of the vi and all the g1 through to gk. And you can write this function in terms of its Hermite basis. The Hermite polynomials, they form a complete eigenbasis for the Gaussian space. So this and some Fourier analysis tools, analytic tools on top of this gives you this statement, essentially. But yeah, proving that requires some amount of work. But anyway, so let's assume this and try to finish the proof of the variance. So I had that vi square, norm of vi square times vj square times log square k times this term over here. So rearranging summation, I can write this as inner product of vi vj whole square divided by k plus summation over I of vi square whole square, right? So what were these two values that we had? So again, going back to this picture, note that summation over ij of vij whole square is equal to k, and summation over I of norm of vi square is also equal to k. So if I plug this in over here, what do I get? This is equal to 1. This is also equal to 1. So your variance is 2 log square k, right? So any questions at this point? So I guess the most crucial part here is, this is where we crucially use the fact that the total inner product square is small. So this sort of indicates that your vectors are strongly correlated. And this is where we are using this correlation. So if you were to pick, say, some n random vectors in k dimension, they do not satisfy this bound. And that is what we are crucially using here. Okay? So at this point, we are sort of done, right? I showed you that the expected value of the numerator is square root lambda k log cube k. So using Markov's inequality, something like 99% of the numerators are smaller than something smaller than this, smaller than some 100 times this, right? And I can bound the denominator by using Chebyshev's inequality, right? So the expected value of the denominator is log k, the variance is log square k. So the probability that the denominator is at least log k over 2 is something like 1/4. So a constant fraction of your denominators are large. Therefore, taking the union bound over these two events, there are at least like k over 8 such indices for which the numerator is small and the denominator is large. And that's it. So we are done. Any questions? So
because you don't take care of all the costs, right? You just take care of a constant fraction of the costs, right?
Yeah.
It's a by criteria essentially.
Right. So, well, I've actually proved a weaker theorem for you. I told you that you can get 1 minus epsilon times k. So to do that, you need to do this like much carefully.
Yes.
But right now, this proof only shows that you get like some constant times k sets. Yeah. So that requires pretty much the same ideas, but a little more careful analysis. Okay. So you can also ask this computational question that given a parameter k, I want to find the best k-partition so as to minimize the maximum expansion. Right? So this can be thought of as like a extension of the sparsest cut problem. So this is actually a very tricky problem because so any of the standard SDP formulations that you try, they can have an unbounded integrality gap. They can be as large as you want them to be. So the standard integrality gap is that you'd have like one indicator vector to indicate which set. You'd have like k vectors for each vertex to indicate which set that your vertex belongs to. And using you can really show that this has an integrality gap like as big as you want. And so I'll not say this in much detail, but Kostya and I, we came up with an interesting SDP formulation, which inherently takes care of all the problems that we seem to have with the standard SDP formulation. And using a similar rounding algorithm, we can get an algorithm that outputs 1 minus epsilon times k sets, each having expansion op times square root log n log k. So Mohit, as you had noted, so any upper bound, so an approximation algorithm for this does not imply anything for the min-sum partitioning. Okay. So yeah, that's all I have to say. Probably the most pressing question is, can you lose this bicriterionness in the approximation that we had? Can you get like exactly k sets, k non-empty disjoint subsets, such that each has expansion square root lambda k log k, right?
So your relative gap, the gap you showed one of the first slides, isn't it a counterexample?
No, so that was for a partition. So right now I'm just saying that there should be k non-empty disjoint subsets. I'm not insisting on a partition. So this could just be like k non-empty disjoint subsets. So if you remember the example that I showed, the k cliques would themselves be these k sets that you want. And so another problem that is of interest related to this is the small set expansion problem, where given a parameter k, you want to find a set of size n over k which has the least expansion. So what I showed you before is that, so what I showed you today it also implies an upper bound for small set expansion, right? If you find a k-partition, then one of those sets is going to be smaller than n to the it's going to be smaller than n over k. So for small values of k, it is fine, but for large values of k, it can be improved. So like Arora, Barak, and Steurer showed that you can upper bound this phi small. You can find a set of size n over k whose expansion is at most lambda sub k to the c, where c is some constant like 65 times square root log n base k. So here, so this is interesting if your k is like some n to the epsilon, because you essentially lose the log n to the base k factor here. So if you're interested in like sub-exponential time algorithms for unique games, then the k that you're going to plug in is going to be something like n to the epsilon. So in that regime, this is more interesting than the theorem I showed you. And that's it. Thanks for coming, and I'd be glad to take questions.
Questions?
You have always examined the number of edges from Si to the rest of the graph. Are there any results in which you care about the edges between Si and Sj, or all pairs Ij, which would be much more?
So that would be like some regularity partition.
I don't know what you mean by that, but
Well, so there's this thing like semi-ready regularity and stuff. Yeah, I haven't seen any problems like the ones that you described.
One could answer, what you want is small expansion into each,
Right.
which is a much stricter condition.
So
Yeah.
you want to look at the maximum of these k-square pairs and minimize that?
For example, or I take some norm of the sequence, or whatever. There are millions of questions.
But you want to look at this the k-square dimension vector and do something
Yes,
with this.
yes, exactly. And even just taking L infinity is much harder.
Yeah, I doubt if it has any connections to the eigenvalues, but
And why the obsession with eigenvalues? I mean, it's nice to have, okay, so, but why? What's the aim? I mean, is the aim to connect locate eigenvalue to partitions or to learn about partitions?
well, the reason why we started looking
the latter. I thought your aim is to learn about partitions.
right. So
You
the reason
happen
why
to
we
know
started
about-
looking
and
at this
you happen
problem.
to know about one method, the eigenvalues.
Yeah, so I'm just saying, yeah. So
It's not compulsory.
right. But yeah, the reason why we started looking at this is because of its connection to unique games. So generally, if you like I said, so if you get like better bounds for this, you could get like slightly better algorithms for unique games. So that is why all this. That is why the small set expansion problem gained fame in the first place.
Also, I would say, so if you're interested in partitioning, then computing eigenvalues is rather quickly. So that's what people do actually in practice to partition data.
I know also there are templates for the method, so of course you
It's
know
one
what
of
to
the
do.
few things that seems to be computationally tractable.
I know, but it's the answer is we do it because we can.
Yeah, pretty much.
Because maybe we're curious, those algorithms that are really implemented, how well they can work if we fix something in this algorithm. More questions? Maybe more suggestions of new problems? That's even better. Well, thank the speaker again.